now a constant or it becomes zero? Change in velocity by unit length.
dv dz equal to 0. Okay, not average. dv x bar by dz, dv y bar by dz, and dv z bar by dz equal to 0. Okay. For fully developed, you have velocity as a vector to be a function of time, right? Only time. So partial derivative of velocity with respect to length from the inlet is 0. Good. Steady state means partial derivative with respect to t equal to 0. That's steady state. Doesn't change with time. Doesn't change with length. Is fully developed or not fully developed. Alright. Let's take a look at flow pattern map. Okay. This is for air water flow at STP. Okay. If it is oil, the map will change, right? You have to play with the map, right? Did you do homework? Submit it. Okay. When you check the viscosity, the map change. Why do you think the map change, Akin? When viscosity go up, this line kind of change, right? Why do you think it changed?
Because buoyancy. Sorry, absorption force.
Because several of the equations that we use is about viscosity. Look at this. Transition C. That's a viscosity term, right? Okay. What about transition A? Is there anything about viscosity? How do you get HL? That's come from the chart, the plot between X and Y, right? X is dependent on viscosity, right? So equilibrium liquid height is based on Reynolds number, friction factor. So that's liquid viscosity. So that's it. Oh, you will notice that none of your transition correlation or equation has any pressure or temperature. Do we have pressure and temperature in transition A formula, transition B formula, transition C, transition D? No temperature, pressure. Okay, series tidal Douglas model, does it account for temperature and pressure? No. Une, does it account for temperature and pressure? Vegard, yes or no? So it already accounts for temperature and pressure effect. So this model, even though it doesn't show you depend explicitly on temperature or something, it is already account all those things through fluid property. And at the end, it's not about temperature and pressure, right? It's about at that condition, what is the fluid property, right? Okay. One thing that we don't have from tidal Douglas model is we cannot discern the difference between elongated bubble and slot. They say everything in this region is intermittent flow, but their model doesn't tell that this part is elongated bubble and this part is slot, but measurement tell. Okay. I is intermittent, SS stratified smooth, SW stratified wavy, DB dispersed bubble. So this chart work for any kind of fluid property. Of course, you have to recalculate everything, right? But this chart will work just for air, water. Oh, cannot delete. Cannot do anything. Sorry. Okay. take a look carefully. This one is horizontal. When I increase the angle, you see, so when we increase the angle, intermittent region become very big, right? First is that small, and then it become very big. First it is like this. This is horizontal. When we have 0.25 upward pipe, just 0.25, a little bit upward, flow pattern map change completely. See that? So flow pattern map is very sensitive to inclination angle. Okay? It's very sensitive to inclination angle. So different pipe diameter, we have different kind of flow pattern map. When we have a bigger pipe, stratified wavy region, the right hand side is 2 inch, left hand side is 1 inch. 2 inch have larger region for stratified wavy. Right? Okay. Increase a little bit, 0.5 upward. Okay, look at stratified wavy region. Does it shrink? Kind of. 1 degree, 2 degree, 5 degree become very small, right? 10 degree. And if I go, okay, this is 10 degree. So when we incline the pipe, mostly we have intermittent flow. When it is upward flow, we have intermittent. What about downward flow? -1. Stratified wavy region go over the part of stratified smooth. You can see this, right? And so what else? After we do this, okay, that's good. -5, stratified smooth is gone for small pipe. Bigger pipe, we still have stratified smooth. See? -5, -10, no stratified smooth, it's stratified wavy. This -10. So the majority of the flow pattern for downward flow is stratified wavy. Okay? So if you want to guess, in slightly inclined pipe, what kind of flow pattern do you typically have? Intermittent flow, right? For slightly downward flow pipe, you have stratified wavy. Okay, look at the cover of your book. That is give you that message to you? Oh really? Look at the cover again. It is a pipe, right? And there's a flow up region. Is that intermittent flow? Yes. What about flow down? Stratified flow, right?
No, Professor, I have two questions.
So I cannot even allow you the book because the cover of the book itself gives you some information, okay? So in the test, don't take the book out of your bag, okay? Yes?
When I was reading Untitled Chapter, I think it's Untitled Chapter, they mentioned something related to this, the gain of in pressure going outward, and no consider pressure loss in downward. So if we are in the
Is that true? As a rule of thumb, you can do that. As a rule of thumb, flow up, we have pressure loss. Flow down, we don't gain any pressure for two-phase flow. That's a rule of thumb. You can actually do the calculation. We haven't gone through any pressure calculation yet. We are about to. Okay.
Yes, because the point is,
yes.
If we are in the industry, if we want to determine the pressure profile in the well,
okay.
So what does the software do? Every time that the
software okay. What does the software do? So if you are in the industry, so most of the time you use Olga. The software will solve system of partial differential equation, use a certain of algorithm. I think they use 2 fluid model for transient flow. They solve everything and give you the pressure drop. That's what the software do.
But for example, when they determine that the fluids are moving downward in any section, does it calculate pressure drop?
It do. It will. It calculate everything rigorously.
And what would be a suggestion? Let's say we have 10,000 feet. So
I would like to.
What would be a suggestion?
I don't want you to like be discouraged in asking question. I will answer that question. How about wait for a little bit when we are in that section? Okay. We are about to tell you how to do pressure drop. It is somewhat time consuming or maybe complicated. Okay. All right. So at the end, by now I hope I gain your trust that the model can predict the flow pattern for minus 10 to 10, horizontal and near horizontal. So in the flow pattern prediction, we assume tau I equal to tau G. That is in the flow pattern prediction, right? So in actual stratified flow calculation, we should use this. Tau I equal to half Fi rho relative velocity square. And you can change Vi to VL. That is in the actual calculation. In the flow pattern prediction, we don't need that accurate. Okay. For stratified smooth, okay, Untitled Chapter suggests assume Fi to be the same as Fg and tau I to be the same as tau G. Okay. So this is still valid if Vg a lot greater than VL. Look at this. If Vg a lot greater than VL, this term kind of gone, right? So if it is stratified smooth, let's do this assumption. Okay, that's that model.
Do we have liquid gas surface tension?
Do we have? No.
But the question is in that in the homework you show on software you needed that.
You needed that. Okay. If you change that, will the answer change? Yes.
Yes, so where is the
So the software and this model, they are not the same. Ta-da! Got it, right? It's not the same. This model doesn't have surface tension.
show how much is different?
Oh yes, we will study that. It's not the same. It's not that different. It use some part of this.
Is it in his book?
Of course, it is in this book. Okay, for stratified wavy, there are several correlations, but what's suggested by Shoham and Title is Fi equal to 0.0142. Interfacial friction factor equal to that number. Put it there, most of the time it's correct, flow in the pipe, no problem. How do they get this? Experiment, closure relationship. The model have prediction of everything, but some part of the model need measurement. And for stratified flow, that part of the model that needs measurement is interfacial friction factor, Fi. How do we get Fi? Oh, I don't know. So for stratified smooth, we assume Fi equal to Fg. And tau I is about tau G. So if Vg is not that much greater than VL, like Vg is 1.5, VL is 1, you may not want to drop this one. You may not want to do that. Okay, you may just do that. Okay, if Vg is not a lot greater than VL, Vg minus VL square is not quite the same as Vg square. But in many cases, you can drop. Okay, in the homework, if you drop or you don't drop, it's fine. In the exam, if you drop or don't drop, could be fine. But when you do measurement, you want to understand that whatever you do with the gravity equation, any assumption, impact the accuracy of your answer. Alright, interfacial friction factor, if it is stratified wavy from the wave, then we say Fi equal to 0.142. That's from measurement. That's one model. Another model is Shaw et al. 1990 suggests and Ritos and Haranti correlation for small diameter pipe and Baker et al. For large diameter pipe. So for small diameter pipe, what they suggest is calculate VSGT. So VSGT is superficial gas velocity for the transition. P is the absolute pressure in Pascal. So if VSG less than VSGT, we use Fi equal to Fg, stratified smooth flow exit. If VSG greater than VSGT, use this formula. Fi over Fg equal to 1 plus 15 square root something. So this is closure relationship to get interfacial friction factor. Okay, there are several ways. So if diameter greater than that value, so okay, now you may have to do several things. Then you have to calculate Weber number NWE and mu, NWE and mu defined like this, okay, and epsilon I defined like that. Now it has sigma, interfacial friction factor, surface tension. Okay, absolute interface roughness should be bound between the pipe roughness and 0.25 of square root h over d. That is the upper limit and lower limit of the interfacial roughness. So if you use Chao et al. Yahweh, how do I pronounce this in Chinese? Chao? Xiao? Xiao. Okay, I think this is Chinese name. Xiao. For that, then what we have to do is first we calculate NEWE, Weber number, viscosity number, and this thing, if you know liquid height, we can do the calculation, right? We can have epsilon I from this formula. From epsilon I, put it there, calculate that. So if this condition satisfy, we use that as an epsilon I. Otherwise, we go another one. And from this, then what's next? It's a lot more. Okay. So what correlate? Okay. What correlation do you think is easier? 0.0142. That's easier, right? Because the wave is kind of a certain form, a certain pattern of the surface. 0.0142 is good. Otherwise, we have to calculate roughness, right? After you get roughness, then we get roughness of the interface. After you get roughness of the interface, then what? Use Kroll equation or explicit form from Hall. Put that roughness that you get over there, then get the friction factor. Okay. So friction factor will require Reynolds number, but that this time will be actual Reynolds number of the gas phase. Rho Vd over mu, and diameter defined like this. So after we have roughness from this model, so if the pipe diameter is large, we get roughness from this model. Depending on this value, this kind of implicit form a little bit. Is it implicit? Could be. So then we do calculation, and then liquid velocity is substitute for the interface velocity. So actually this has to be VL. So they use liquid velocity instead of gas velocity liquid velocity instead of interface velocity. Which page number that has this formula? Come on, come on, come on. Raymond, open the book, open the book. Go to that page. Have you? The book have it? Your book have something like that? You find it? Not yet. Search for it. I think maybe it's at the back. Okay. It's fine if you cannot find it now. But this one, we should have it. Do you have it? Ouyang and Aziz, Walsh stress. So this term is for Raymond, you find it?
14. So at the end of the third chapter, we can find the shell model, right?
And do you have that?
And we just have these four.
Okay. It's somewhere in the book. Okay, let's talk about Walsh stress. I put here that Tytler phase hydraulic diameter and friction factor using standard method is valid only for gas phase only. So for gas phase, we do everything as usual. Okay. Ouyang and Aziz suggest use something different for liquid phase. Okay. Liquid wall friction factor can be affected significantly by the interfacial shear stress, especially for low liquid hold-up condition. So for low liquid hold-up condition, they suggest another form of friction factor, this one. Do you have this formula? Which page? 84. Okay. Akin, you find it on 84? Or his book has it, but your book doesn't have? Okay, it's there. So for low liquid hold-up, they suggest something else. What do you use? You use the easiest one. You don't need to do this. Okay. It will be more accurate, but how much more accurate? So you may use something like that. They said it can be impacted by interfacial shear stress. If you want to do rough approximation, you don't need to care anything about this. Okay, nothing about this. Then use just regular way of calculate shear stress. Okay, it works and correct. But for low liquid hold-up, this may be better. Okay. So calculation procedure. Fi for stratified wavy 0.0146, right? If it is smooth, Fi equal to Fg. So first step, we predict the flow pattern. If the flow pattern is stratified flow, then determine X and Y, determine HL from the full form of dimensionless combined momentum equation. What does it mean? What is full form? First, we get the flow pattern. After we get the flow pattern, we know that it's stratified flow. We redo it again. This time, when we redo it again, we use the full form without the assumption that Fi equal to Fg. If we don't use the assumption that Fi equal to Fg, we have this form of the equation, right? Okay. Or you can solve it from dimensional form directly. That is dimensional form. So, to get HL. The reason that we may have to redo it because you remember the chart, this graph that you get from Tytler, this graph from Tytler, there's an assumption over there, and the assumption is Fi equal to Fg. That is the assumption to generate this chart. Because at that time it is what? 1976. 1976, you don't have a computer. Do we have a computer? I don't even know. You may have big computer. We cannot really calculate everything, right? So they made some assumption to do for the calculation. So when we have that assumption, it's kind of simplify everything. Okay, Fi equal to Fg, tau I equal to tau G. It simplify everything. Where did it simplify? Okay, multiply by -1. See this one. So this, after we use this part, tau Wg equal to tau I, we get a simplified form. But you know, by doing previous homework, that you can work on the full form without any simplification, right? You don't need to assume tau I equal to tau G. You can use actual form, which is too quick, sorry. We can solve the full form of momentum equation and try to get HL tilde directly. So this time your tau I will be Vg minus PL, everything square, 1/2 rho and F, right? So you can solve the equation full form numerically directly and get the value of HL. That's the next step after the flow pattern is determined. After that, solving the dimensional form. Solving tau Wg, rho G, Fg, Reynolds number, velocity, everything. Okay. Do the same for liquid phase. Because tau Wg and everything else is a function of liquid height. After we get every parameter, then we calculate, estimate interfacial friction factor. If it is stratified wavy, use that, just the top one. Okay, it is correct enough. Okay. The second one, all this is your choice. Okay, but I suggest this. That's very good already. If it is stratified wavy, we calculate Fi from that. If it is stratified smooth, Fi equal to Fg. Okay, and then calculate hold up from Al over Ap. Okay, after calculate hold up, then we can calculate pressure drop per unit length from either dPdL subscript L or dPdL subscript G. Pressure drop per unit length in the gas phase and in the liquid phase, they are identical. They're the same. Okay. So in the exam, what do? You calculate x, you calculate y. You use the chart to determine the HL tilde. From HL tilde, you check transition A, transition B, or transition A and transition C. And if it is stratified wavy, we use Fi equal to that. Okay. After that, calculate tau WL, tau WG. Arya Shadi, how do we calculate tau WG? What is the formula to calculate tau WG?
The same formula for friction.
Tell me the formula. Not the same formula to something else. Tell me the formula to calculate tau WG.
So the Fg used the velocity
Tau WG equal to what?
equal to
Which page number? Open the book. Oh, you don't have the book. Okay, Yao Sheng. Tau WG. You don't have the book? Akin. Tau WG equal to what? 0.5 F rho v square. Did I give you any of that formula early on? In the very early,
you use Multi?
we have this formula, right? Tau WL 1/2 F rho V square. This is this Moody or Fanning? This is Fanning. This is
We have 2F.
that is for minus dPdL. Okay. This is Fanning. Okay. Use that. So after we use those formula, almost done. We get tau WL, tau WG, tau I. We have to, if it is, you should do it at more accurate version. More accurate version is instead of Vg square, use Vg minus VL, everything square. That is tau I square. 1/2 rho Fi and Vg minus VL square. That will give you tau I. Good. So all this stuff is known. What do we do? I don't think so. Tau I, what do we typically use? 1/2 Fi rho G. Okay, rho G. Relative velocity square. So once we know every term, move this to the right hand side. Then we get pressure drop per unit length. Done. Okay. And that will be pressure drop per unit length for stratified flow. Good? Can you do it? Of course, not this exam. Exam after this. Or should we put in this exam so next exam will be easier? This is very lengthy calculation if you notice. Because to get the flow pattern is a long process already. Get X, to calculate just X, it takes you 15 minutes. Don't you think so? You have to convert from volumetric flow rate to velocity, from velocity, get Reynolds number, get friction factor for gas phase, get friction factor for liquid phase, then get capital X, get capital Y, use the chart, get the flow pattern, check transition A, check transition C, calculate, check transition K, then put everything in here. It could be like 1 hour to do this. Especially if you don't use Excel, if you do by in exam. Yes?
We have 18 minutes to the exam, so how many questions are there? How many?
Oh, I don't care. I can put as many questions as I want, and at the end, what I do is the highest score, then we can use my 120 minus the highest score or something. But most of the time, my question, I make it such that first 2 students can get 120. Yeah. It's not going to be difficult. The reason for making the exam is to check whether you are very good or you are excellent. I don't want to check that. I want to check if you know, you don't know it. Okay, just that. I still have 3 minutes. Do you want to do slab flow?
No,
I have a question. So if it breaks down, if you are able to determine that it's not either A or C, that means we cannot, based on that, we cannot calculate the result, right?
If it is,
when we check and if it's not A or C, if it goes to maybe K, we can't calculate the result there from this formula.
transition K will tell whether it's stratified smooth or stratified wavy, right?
Okay.
If it is double flow, we check transition A, it is stratified. We check transition C, is not stratified wavy. We check transition K, it is stratified wavy. Then we assume that it's stratified wavy. If the differential friction factor is 0.0146.
if it is stratified, they accept.
If it is stratified, whatever flow pattern that you get, you have to accept it, okay, from the model.
But if I'm saying you don't check K.
If it is stratified wavy,
It's stratified.
you check transition A, right?
Yes, this is and C, and now we know that this is stratified.
Stratified smooth or stratified wavy?
We check A.
We check A, we will know that it is stratified or non-stratified. That is what we get after A.
So
Then we have to check whether it's smooth or wavy.
Yeah, it's smooth.
Is it horizontal or downward? If it is downward, you still have to check transition K.
What about stratified wavy?
If it is stratified wavy already, you don't need to recheck transition K.